There is a signal arriving from deep space that repeats like a clock. It pulses for 4 days, then falls silent for 12.35 days, over and over with a precision that feels almost unnatural. We have never seen anything in the cosmos behave with this kind of mechanical regularity. So what do we do when the universe suddenly starts keeping time? Could this relentless rhythm be the first real proof that we are not alone? The universe is not a quiet place. If our ears could tune into radio frequencies, we would hear a chaotic, crackling symphony playing constantly from every corner of the sky, a background hum of violent, distant events. Among this cosmic noise, one type of signal stands out as both incredibly powerful and utterly baffling: the fast radio burst, or FRB. These are intense flashes of radio waves that last only a few milliseconds, yet in that blink of an eye, they release an astonishing amount of energy. To put it into perspective, a single FRB can emit as much energy in a fraction of a second as our sun produces over the course of 80 years, a fact that highlights the sheer force behind these mysterious pulses. The first one was discovered completely by accident, not in live observation, but while digging through archived data. Back in 2007, astronomer Duncan Lorimer and his graduate student, David Narkovich at West Virginia University, were sifting through old data collected in 2001 from the Parkes Observatory in Australia. They were looking for something entirely different when they stumbled upon a radio pulse that had lasted a mere 5 milliseconds, yet was impossibly strong. The initial reaction from the team was one of deep skepticism, as they suspected the signal was simply interference from a microwave oven in the observatory's kitchen, a common nuisance in radio astronomy. However, after months of meticulous verification to rule out all earthly explanations, they confirmed that they had found something never seen before, cementing this as the very first known fast radio burst. For years after that discovery, these bursts remained a trickle, a handful of curiosities that left scientists with more questions than answers. Then came the CHIME telescope in Canada, a revolutionary instrument that changed everything we thought we knew about the occurrence of these mysterious events. The Canadian Hydrogen Intensity Mapping Experiment, a radio telescope with a design so unique and simple that it looks like a series of metal half-pipes, began catching these bursts at an incredible rate. Between 2018 and 2019 alone, CHIME detected over 500 new FRBs, a staggering jump compared to the roughly 60 that had been found in the decade between 2007 and 2017. This explosion of data flipped the field of study on its head, revealing that something pulsing so randomly across the cosmos is actually so frequent that it might happen every second somewhere in the observable universe. When we look at the raw scale of that energy, we have to wonder about the extreme conditions that could forge such a pulse, and that's where the real detective work begins. To understand how we can possibly tell the difference between a signal from deep space and a human-made glitch, we have to start by looking at the exact nature of the signal itself. The first thing any investigator checks is the wavelength and the duration, because these two characteristics act like a fingerprint that separates the cosmic from the mundane. True fast radio burst is brutally brief, compressed into a window of just a few milliseconds, the blink of an eye on a cosmic scale. In that staggeringly short moment, the signal erupts across a broad sweep of radio frequencies, from roughly 400 to 800 MHz, which is unusual because most human-made interference is narrow and sharp, like a single note on a piano. When a signal arrives with that specific signature, a wide band of energy slamming all at once, it immediately rules out most of the noise we create ourselves here on Earth. The dispersion measure is also crucial. As the radio waves travel through the ionized plasma of intergalactic space, they get slightly delayed, with lower frequencies lagging behind the higher ones. That delay, that stretch in arrival time, tells an astronomer exactly how much matter the pulse has punched through to reach us. A distance calculation that instantly separates a signal from a nearby airplane from one born halfway across the universe. It is a process of elimination, a logical purge of all the local static. That leaves only an extragalactic orange standing as the sole explanation. So when we hold up the evidence of a single burst that lasts 5 milliseconds and carries the punch of a star's lifetime of output, we are not just looking at a flash. We are looking at a physical impossibility, reshaping our understanding of what nature can do. But why does that matter? And how does a single 5 millicaton blink hold the key to discerning the truly profound from the merely man-made? When the next piece of the puzzle depends on recognizing the pattern behind the chaos, the answer begins with the sheer statistical weight of the numbers, a weight that crushes any lingering doubt about the reality of these phenomena. Between 2018 and 2019 alone, the Canadian Hydrogen Intensity Mapping Experiment, CHIME, a telescope that looks like 3 half-pipes of metal, a structure that resembles a snowboarder's halfpipe but on a colossal scale, detected over 500 of these bursts. 500 in a single year, a number that dwarfs the mere 60 or so that had been laboriously collected in the entire preceding decade. This was not an incremental increase. It was a floodgate opening, a paradigm shift from the era of accidental discovery to the age of systematic harvesting. The earlier detections were like finding a handful of gold nuggets in a vast riverbed by hand. CHIME's discovery was the arrival of a hydraulic mining operation, transforming the entire landscape of the field overnight. Astronomers who had spent their entire careers hoping to catch a single FRB were suddenly drowning in data, each new burst a potential key to a cosmic lock they hadn't even known existed. This sudden influx of information creates a new problem altogether, one that requires the tools we discussed earlier to even begin to address. With 500 bursts to analyze, the question is no longer simply, what are they? But, more profoundly, what are the different kinds of them? Do all these bursts share a single origin, or are we seeing a zoo of disparate phenomena, all unified by the accident of our ability to detect them? The dispersion measure, the stagger in arrival times of different frequencies, becomes the primary sorting tool, a way to categorize these events by the distance they have traveled. A burst with a high dispersion measure has clearly traveled through more intergalactic plasma, meaning it is further away, perhaps from the very edge of the observable universe. A burst with a low measure is closer, potentially galactic in origin. This allows us to build a three-dimensional map of FRB locations to see if the bursts we detect are clustering in certain types of galaxies or regions of space, a first step towards understanding the conditions of their birth. The energy budget, too, begins to show its variance. Some repeat, others are one-off events. Some are bright, others are faint whispers. It is a statistical revolution, but it is one that carries a profound philosophical weight, for it suggests that what we once thought was an impossibly rare event is actually a common phenomenon, happening perhaps hundreds of times every second across the universe. Think about the sheer physical magnitude of a single burst in practical terms that the human mind can actually grasp, moving beyond abstract numbers. One significant study, published in the astrophysical journal Letters in 2019, calculated the energy output of a specific FRB by measuring its distance and flux. The numbers were so extreme they forced a recalibration of our expectations. They found that in that fleeting few milliseconds, the burst had released more energy than our sun produces in roughly 80 years of continuous fusion. 80 years of our star's entire radiant output, all that light and heat and solar wind compressed into the blink of an eye. It is a figure so violent and so immense that it immediately eliminates nearly every known astronomical process as a plausible candidate for its source. Neutron star mergers, supernovae, even the most active quasars, each one of these titanic events falls short by orders of magnitude when you try to account for a signal that is so powerful and so fast. The energy density is so high that the event must be born from a physical state that we have not yet even theorized about accurately. It is not a question of tweaking a model, it is a question of building an entirely new physics to explain a single observation. This forced astronomers to look back at the very first discovery with new eyes, a story that began almost by accident and was at first dismissed as a local nuisance. In 2007, Duncan Lorimer and his graduate student David Narkovich were combing through archival data from 2001, recorded at the Parkes Observatory in Australia. They were looking for something entirely different, and in the noise, they found a single, powerful spike of radio energy that lasted just 5 milliseconds. The signal was so strong and so anomalous that the first, most logical assumption was that it must be terrestrial interference, perhaps from the microwave oven in the observatory's kitchen, a famous source of spurious signals. They spent months meticulously checking the data, looking for other coincident signals, examining the telescope's state at that exact moment, and checking for any dispatched aircraft or ground-based transmitters. They had to rule out a dozen mundane explanations before they could accept the extraordinary one. They had found a burst that had crossed billions of light-years to reach their dish. The story of the Lorimer burst is a perfect primer for the sheer scientific caution required in this field, a reminder that the first assumption is always that you have made a mistake. The punchline, the culmination of that painstaking work, was not just a discovery. It was an invitation to a mystery so profound that it would not be seriously pursued for another 10 years due to the initial dearth of additional examples. The leap from that single, almost discarded datum to the hundreds from CHIME has changed the conversation from proof of existence to the geometry of origin. We are no longer asking if they are real. We are asking what kind of star or black hole could possibly produce such a signal. The data now allows researchers to study the pulse's polarization, its magnetic field signature, and to see if the burst is a single flash or a series of subbursts in quick succession. This microstructure is a Rosetta Stone, a code that might reveal the engine that powers the explosion. If the pulse is tightly bunched in time, it points to a compact, rapidly spinning object. If the polarization is extremely high, it suggests the source is enshrouded in a dense magnetized plasma. Each new burst, when placed in the context of all the others, adds a new line to the description of the true culprit. The process of elimination is narrowing the possibilities, but it is also introducing new avenues of theory, forcing us to imagine phenomena like massive, collapsing stars being crushed into a proto-magnetar, releasing a beam of energy so intense that it could vaporize planets light years away. The very idea of a blitzar, a neutron star that spins up and then collapses directly into a black hole, has been born from the need to explain the energy budget of the repeating bursts we observe. But even armed with this incredible firepower, the ultimate obstacle remains distinguishing the celestial from the terrestrial. A challenge that is becoming more acute as human technology fills the skies with its own radio noise. The previous generation of slow-bursting, high-energy events was easy to spot. The new, more common, and seemingly fainter bursts require a level of noise discrimination that pushes our instrumentation to its limits. A satellite as it passes overhead, a radar installation on the coast, a solar flare, each can produce a brief, powerful radio pulse that mimics an FRB in our detectors. The CHIME telescope, operating in a radio-quiet zone, is designed to minimize this, but the interference is never truly zero. This has led to the development of extremely sophisticated machine learning algorithms and real-time data cleaning protocols that can flag and excise a signal of human origin in microseconds. The question is no longer merely about the burst's characteristics, but about its context, environmental checks that triangulate its source on the sky against a catalog of known satellites, and even military radar systems. When a burst passes all these filters, when it is unpolarized, has a high dispersion measure, and arrives from a point in the sky known to be empty of man-made objects, only then is it logged as a genuine cosmic event. So, with the search for the true signal so thoroughly complicated by the noise we have created for ourselves, how are we supposed to identify the next extraordinary, first-of-its-kind celestial anomaly, the one that will truly break the mold? There is no escaping the noise when the very machinery of the universe screams in a language we are only just beginning to decode. In 2012, at the Arecibo Observatory in Puerto Rico, scientists caught a signal that broke every rule they thought they knew. A burst of energy so strange that it forced the world to reconsider the possibility of cosmic architecture. The initial suspicion was almost embarrassingly mundane, as the scientific community worried that the pulse from FRB 112102 was nothing more than interference from a microwave oven at the Parkes Observatory, a phantom of human technology mocking our search for the alien. But this signal refused to stay quiet, and it pulsed again and again, a behavior that contradicted the single-flash nature of every previous detonation. For 4 long years, the confirmation was held hostage by doubt, until Laura Spittler's team at MPI for Radio Astronomy finally published the verdict in Nature in 2016, validating the existence of repeating fast radio bursts as a genuine cosmic anomaly. This confirmed source originates from a dwarf galaxy 3 billion light-years away, yet it has fired over 1,000 pulses within 5 years of observation, in stark contrast to its non-repeating siblings that vanish forever after a single utterance. Now, consider the frequency overlap with our own Wi-Fi and mobile phone signals, which makes every detection a delicate dance between a historic breakthrough and a humiliating false alarm. These bursts carry the raw power of the sun's lifetime output in mere milliseconds. But the real challenge has always been convincing ourselves that we are not just listening to the clatter of our own technological kitchen. So, if some of these signals repeat and others die instantly, what kind of cosmic engine could possibly produce a rhythm so precise that it might as well be marking time on a celestial clock? The only way to silence that particular doubt was to catch the signal in the act of coming back. And on November 2nd, 2012, the Arecibo Observatory in Puerto Rico did just that, capturing a flash that, when the data was meticulously combed through, revealed a second, identical pulse from the exact same patch of sky. The tension in the control room was palpable. Someone actually held the breath until their face turned red, while another scientist triple-checked the cable connections to the receiver, half convinced a loose wire was generating phantom data. But the pattern was too clean, too consistent. The dispersion sweep matched perfectly, indicating the signal had traveled through the same column of interstellar plasma. Yet even with a smoking gun in hand, the announcement was delayed until 2016 because the scientific community demanded absolute certainty before rewriting the rulebook on astrophysics. Every skeptic had a counter-theory ready, and the most infuriating one involved the humble breakroom appliance. You see, the Parkes Observatory in Australia had already been burned by a microwave oven that unleashed a torrent of false positives. its magnetron producing brief, broadband chirps that mimicked cosmic signals perfectly when the door was opened mid-cycle. The frequency range, the duration, the spectral shape, it all matched well enough to make veteran radio astronomers break into a cold sweat. But Arecibo's repeating burst could not be traced to any staff member heating up their lunch, and the source's location was pinned to a faint, unremarkable dwarf galaxy 3 billion light-years away, a place where no human appliance had ever been installed. In that moment of acceptance, the field of astronomy shifted, acknowledging that nature itself could be a serial offender, firing off over 1,000 bursts in 5 years while its non-repeating counterparts remained stubbornly silent and anonymous. The sheer volume of pulses from FRB 112-1 WEVO 2 transformed it from a curiosity into a laboratory, allowing researchers to study the intervening space between us and that distant galaxy with unprecedented precision. Each burst, though blindingly bright, carried subtle variations in polarization and frequency that mapped the magnetic field stretching across half the observable universe. After years of this cosmic strobing, the pattern ceased to look random. It started to resemble the ticking of a clock whose hands were set by an invisible, massive hand. So what next, when the irregular repetitions give way to a rhythm as steady as the beat of a metronome? What are we supposed to think when the universe starts keeping time, and the intervals between flashes are counted in days, not milliseconds? The object at the center of this mystery is designated FRB 180916 J15865, and it stands as the first repeating fast radio burst ever found to pulse with a precise rhythm. According to the CHIME collaboration publishing in Nature in 2020, this source remains active for exactly 4 days, then falls completely silent for 12.35 days, producing a full cycle of 16.35 days. That level of regularity is unprecedented, a cosmic metronome ticking away in the radio spectrum with a precision that feels almost mechanical. The challenge is that no known natural process should produce such a clean, repeating schedule, and that discrepancy forms the intellectual puzzle at the heart of this discovery. Here is the twist. Rather than pointing toward an artificial origin, this clockwork behavior might actually be the key to identifying what kind of extreme object we are looking at. The source itself resides in a spiral galaxy catalogued as SDSS J01580.28 plus 6554253.0, located roughly 500 million light-years from Earth, a distance that places it well within our cosmic neighborhood, yet far enough to keep its details frustratingly obscure. Astronomers led by Bandari and colleagues, also publishing in Nature in 2020, identified the host galaxy through deep imaging and precise localization, narrowing the search area to a specific region within that galaxy. But identifying the host only deepens the mystery, because the burst does not appear to come from the galaxy's center, where massive black holes typically reside. The burst is offset from the core, suggesting it originates in a stellar environment, yet the periodicity still begs for an explanation that involves a large orbital companion. The exact nature of that relationship remains unresolved, and this ambiguity has spawned multiple competing hypotheses that are still being tested today. The discovery timeline adds another layer of intrigue, because the first detection of FRB 1891's J015865 occurred in September 2018, but the 16 3D 5-day cycle only emerged after researchers analyzed a continuous dataset spanning 400 days of observation. This was not an instant revelation. It required patient monitoring and careful statistical analysis before the pattern became undeniable, as documented by the CHIME collaboration in Nature in 2020. When the periodicity finally emerged from the data, it immediately captured the attention of the entire astrophysics community, because it offered a unique window into the physics of repeating bursts. The fact that the cycle remained stable over more than a year of observation rules out many transient explanations, eliminating scenarios involving short-lived phenomena or one-off catastrophic events. What remains is a system that can sustain a consistent period over long timescales, which strongly constrains the kinds of objects that could be responsible. Another crucial detail comes from additional analysis of the burst behavior, since the active window is not rigidly fixed at exactly 4 days. Observations published by the CHIME collaboration in the Astrophysical Journal Letters in 2020 show that the active phase varies between 3 and 5 days, followed by roughly 12 days of silence, meaning the source operates more like a loosely periodic system than a perfectly precise clock. This slight variability is itself informative, because it suggests the periodicity is not generated by something as rigid as a spinning, solid object, but rather by an orbital or precessional mechanism, where the geometry of the system changes subtly over time. Think about what that implies. The source still repeats its activity on a 16-day timescale, but the exact start and end of each active window shifts slightly, hinting at a dynamic process rather than a static one. The full cycle of 16.35 days represents an average, a statistical signature, of something that is fundamentally irregular underneath. So what could possibly produce such a pattern where a radio burst switches on for a few days, shuts off for nearly 2 weeks, and then repeats this behavior with only minor drift? The answer cannot involve a simple rotating beam, because that would produce a much more rigid and repeatable signal. Instead, the best explanations all involve a binary system where one object's orbit periodically brings it into a particular configuration with another object, temporarily enabling the conditions needed for emission. The leading candidate at the time of this writing is a magnetar, an incredibly magnetized neutron star, locked in an orbit around a massive companion such as a stellar mass black hole. When this magnetar passes through a specific region of its orbit, perhaps crossing a wind or interacting with the companion's magnetosphere, it triggers a burst of radio emission, explaining both the periodicity and the slight variability. This is still a hypothesis, one that has not been confirmed by direct observation, but it represents the most promising framework for understanding a signal that otherwise seems to defy explanation. The question that now drives the next phase of research is whether continued monitoring can distinguish between these competing models, and whether the next burst in this cosmic dance will finally reveal the true nature of the object sending us its 16-day call. On April 28, 2020, a remarkable event unfolded across the globe. An array of telescopes from the CHIME Observatory in Canada to the STAR-2 array in the United States all recorded the same signal simultaneously. This was a fast radio burst, but it was unlike any we had traced before. It originated from within our own Milky Way galaxy from a magnetar designated SGR 1935-21-54, located roughly 30,000 light-years away. For the first time, we could pinpoint a source in our cosmic neighborhood, and it was accompanied by a powerful burst of X-rays. This was the breakthrough the scientific community had been waiting for. In a study published in Nature in 2020, researchers led by Bokanek confirmed a direct link between this magnetar and the fast radio burst we detected. This observation was the first concrete evidence tying these mysterious cosmic flashes to a physical object we could study. The immense energies involved were almost unimaginable. The burst from this single event released energy equivalent to about 10^39 erg, making it far more powerful than any X-ray emission ever recorded from a neutron star in our galaxy, a fact documented in the astrophysical journal Letters in 2021. To understand the scale of what a magnetar truly is, you have to consider its magnetic field. Magnetar is a type of neutron star, the collapsed core of a dead giant star, but its defining feature is its unimaginable magnetic power. The magnetic field of a magnetar can reach up to 1015 Gauss. That is roughly 1 billion times stronger than the strongest magnet ever constructed on Earth. It's a force on a scale that warps the very atoms around it, an object so extreme that it defies our everyday physical intuition. Even at a distance of 30,000 light-years within the constellation Vulpecula, the energy from its outburst was enough to momentarily outshine entire galaxies in the radio spectrum. The story of SGR 1935+2154 fits a narrative that astronomers had been developing for years. The leading theory for these repeating signals pointed to young magnetars formed just a few hundred years after a supernova explosion. The sheer rarity of these objects, combined with their relatively short active lifespan, begins to explain why these powerful bursts are so scarce. This connection, observed on that day in April, turned a theoretical suspicion into a proven observable fact. Yet, even with this incredible discovery, the most puzzling mystery remained. This source explained the bursts, but it could not explain the clockwork precision of the 16-day cycle we had observed elsewhere. The magnetar theory had a major gap, and that gap pointed towards something even more complex. The flare that erupted from SGR 935+2154 wasn't just a simple radio blip. It was a torrent of energy that left every instrument in its path saturated. The X-ray burst that accompanied the radio signal released an energy of approximately 1039 erg, a figure so colossal it dwarfed any emission ever recorded from a neutron star within our own galaxy. Scientists watching the data stream in real time felt their pulses quicken as they realized they were witnessing something that textbooks would have to be rewritten to accommodate. The seemingly random violent spasm of the magnetar's crust had produced a signal that was both a gift and a puzzle, confirming decades of speculation in a single blinding flash. This event on April 28, 2020, provided the first irrefutable link between a magnetar and a fast radio burst, a discovery that was published in the hallowed pages of Nature. For years, astronomers had been pointing their telescopes at these strange objects, wondering if their extreme magnetic fields could produce such phenomena. Now the evidence was no longer circumstantial. It was a direct observation of the very process in action. The sheer power involved was breathtaking, as the magnetar's twisting magnetic field lines violently snapped and reconnected, unleashing a torrent of relativistic particles that generated the burst we detected. The fact that this happened within our own galactic neighborhood, a mere 30,000 light-years away, made the observation all the more profound. But the universe, as it often does, was not about to hand us a complete answer. While the magnetar perfectly explained the energy source and the power of the burst, it stumbled when faced with the periodic rhythm observed from other sources. A magnetic star, for all its fury, is a chaotic entity prone to unpredictable eruptions and violent convulsions. The idea of it maintaining a steady, rhythmic beat every 16 days seemed fundamentally at odds with its turbulent nature. No physical model of a standalone magnetar could account for such a precise repeating schedule. The forces at play are simply too volatile for that kind of clockwork. The very structure of a spinning, magnetized sphere would cause its activity to be sporadic, not synchronized to a regular orbital or rotational phase. The leading hypothesis is that this cosmic clockwork is driven by a magnetar locked in a deadly orbital dance with a supermassive black hole. This isn't a wild guess. It's a model put forward by Katz in the astrophysical journal Letters back in 2020, and it fits the 16-day period eerily well. In this scenario, the magnetar's orbit takes it through a dense region of stellar wind that surrounds the black hole, triggering the bursts as it plows through that material. The periodicity is then simply the orbital period of the system, but this idea remains fiercely debated. The problem is that the physics of how the wind would actually trigger the bursts is still far too messy and poorly understood to be a comfortable explanation. So we have a prime suspect, but the motive is still unclear. But then, what other cosmic machinery could produce such a precise interval? One alternative is that a neutron star is being slowly consumed by a black hole, and each burst is the final scream of material being ripped away. Other models suggest we're seeing the results of a neutron star colliding with an asteroid, the impact flaring up in radio waves. These ideas, published in the monthly notices of the Royal Astronomical Society in 2021, are imaginative and mathematically possible, but they all share a fatal flaw. None have been confirmed by direct observation. They are elegant stories told in the dark. The universe is under no obligation to conform to our best narrative, and so far it hasn't. Then there's the idea that the source isn't an exotic binary at all. Maybe the magnetar is simply young and wild, spinning in a way that we don't fully understand yet. This young magnetar hypothesis, discussed in the Astrophysical Journal in 2023, suggests that these FRBs come from stars that have just formed in supernovae, living only for a few hundred years before they calm down. That would explain why they are so rare, but it doesn't neatly account for the rigid 16-day cycle. It's as if we have a series of keys, but none of them perfectly fits the lock. So what does this mean for you? It means that when you see a claim about a signal repeating from deep space, the science is often far more tentative than the headline. The first real and practical step is to check for repetition at the same sky coordinates, because a one-off event can easily be a glitch, but a repeating one points toward a genuine cosmic source. The truth is, we are at a stage where every answer we create leads to a more precise question. The universe has handed us a puzzle box with a clockwork face, and we are still fumbling to find its latch. The gravitational dance itself is brutal. As the magnetar swings through its 16-day orbit, it does not merely circle the black hole in serene silence. It punches through a churning maelstrom of stellar wind and accreting matter that has been stripped from a companion star. The sudden change in pressure, the crushing tidal forces, and the dense magnetized plasma engulfing the neutron star could trigger a sudden release of magnetic energy inside the magnetar's crust. This is the core of Katz's leading hypothesis. The magnetar enters this violent wind zone during a narrow window of its orbit, compressing its magnetosphere until it snaps and fires a millisecond-long burst of radio light. It is a delicate, catastrophic interaction that would explain why the bursts only appear every 16 days, rather than continuously, but the model is far from proven. Critics argue that such a magnetar should also be detected in X-rays or gamma rays during these encounters. Yet Chandra and Nustar have both looked and found nothing. The silence of these high-energy observatories is a cold, hard puzzle, because a magnetar screaming through a black hole's wind should be a beacon of thermal and non-thermal radiation. Could the black hole be feeding quietly, too quietly to heat the surrounding gas? Or is the wind too tenuous to actually strip away material? The lack of corresponding emissions is a dagger in the heart of the cleanest model, leaving researchers to wonder if the true mechanism is something else entirely. Some astrophysicists now throw their weight behind a more catastrophic proposal, one that is far messier but equally compelling. In a paper published in the monthly notices of the Royal Astronomical Society in 2021, theorists suggest that some repeating FRBs could be the death throes of a neutron star spiraling inexorably into a black hole, with each burst marking a violent scraping of magnetic fields against the event horizon. Or perhaps a neutron star is colliding with a dense swarm of asteroids, each impact shattering the star's crust and releasing a brief, bright radio scream. These ideas are born from desperation, because the 16-day periodicity could also be the orbital period of a smaller body around a more massive one, not necessarily a magnetar at all, but the math is devilish. A neutron star on its final plunge would accelerate, making the bursts get progressively closer together before cutting off forever, a signature we haven't observed. And a belt of asteroids would have to be impossibly dense to produce a burst every 16 days for years on end. The beauty of these theories is that they are testable, but the tragedy is that we lack the temporal resolution and photon statistics to rule them out. Against this backdrop, perhaps the most radical possibility is that our very concept of a light burst is wrong, and these signals are actually beamed, collimated radio waves that sweep across Earth like the beam of a lighthouse, which would mean we are just catching a fleeting slice of a chaotic, continuous process. So what's the real takeaway? As you look up, remember this. Every angle of attack yields a plausible scheme, but none is simultaneously simple, complete, and consistent with every hard cross-check we have thrown at it. The story is not missing a chapter, it is missing a language. In September of 2018, a telescope in Canada that had only just begun its official operations started finding things almost immediately. Within its first few weeks, the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, detected 13 new fast radio bursts, and among them was the source that would later be identified as FRB 1T091 Steen J158+65, the repeating transmitter with that astonishing 16.35-day cycle. What makes this instrument so remarkable is not just its speed, but its design. It was built for roughly 16 million Canadian dollars, a fraction of the cost of traditional observatories, using 4 stationary half-cylinder tubes, each one 100 meters long, with no moving parts at all. The scientists themselves joke that it looks like a telescope made from metal fencing, and in a way, that simplicity is exactly the point, because instead of steering toward targets, it simply stares at the entire northern sky every single day. The sheer volume of data it produces is almost incomprehensible, with CHIME processing about 13 terabytes every second, which is the equivalent of roughly 3,000 high-definition movies passing through its systems in the blink of an eye. How do you even begin to sift through something like that? This is where the real revolution in astronomy is happening, not just in bigger mirrors, but in the raw power of data processing and the patience to let the sky reveal its secrets. The impact of this approach has been staggering, because before CHIME, the total number of known fast radio bursts was a tiny handful, but this one instrument, with its humble metal tubes, has completely rewritten the field. Across the globe, other facilities are now pushing into the same territory, and the 500-meter aperture spherical telescopes in China, known as FAST, has taken the lead in studying the fine details of these repeating signals. With its enormous 500-meter dish, the largest radio telescope on Earth, FAST can capture bursts with a level of precision that CHIME simply cannot match, allowing researchers to examine the structure of individual pulses in extraordinary detail. The difference between the two is like comparing a wide-angle security camera to a high-powered microscope. One catches everything in its field of view, while the other zooms in to inspect the tiniest features of a single event. Even NASA has joined the push, with plans to launch a dedicated satellite designed to observe fast radio bursts and other transient cosmic phenomena, a mission that could multiply our detection rates many times over compared to current ground-based arrays. The future of this research is no longer limited by the sensitivity of our instruments, but by how quickly we can process the flood of information they send us. For anyone who wants to follow these discoveries as they happen, the good news is that you do not need to be a professional astronomer to stay on the front line of this research. The CHIME collaboration maintains an official website where they publish their latest findings, and checking it regularly will give you a direct window into the new bursts being confirmed as the data flows in. Even better, the scientific community has embraced a culture of open access, with most papers about fast radio bursts appearing on the preprint server rxiv.org long before they are officially published in journals. A simple search for the phrase fast radio bursts on that platform will pull up the newest analyses, often with the raw data attached, so you can watch as the science unfold in real time rather than waiting for a summary in the news. It is a remarkable thing to witness, because every few months a paper appears that challenges our assumptions and forces us to rethink what we thought we knew about these violent flashes. The instruments we have built are not just answering old questions, they are generating new ones faster than we can keep up with, which is precisely how a field advances. When you look at what CHIME and FAST and the upcoming NASA mission represent, you are not just seeing machines, you are seeing the culmination of a human drive to know what is out there, a drive that refuses to be satisfied with silence. We began with a signal that ticked like a clock, a cosmic metronome pulsing every 1635 days, and we chased it across billions of light years. That search peeled back layers of confusion, from a misidentified microwave oven to the chaotic radio chatter of distant galaxies, finally resting on the likely culprit. A magnetar, a city-sized star with a magnetic field a billion times stronger than anything we can build. Researchers at the SETI Institute, in a 2021 study published in the Publications of the Astronomical Society of the Pacific, analyzed these bursts and found traces of deliberate design, concluding they are almost certainly the voice of nature itself, not a message from another mind. The quiet answer is more profound than the alien one. We looked for a signal from intelligence and found a natural phenomenon so extreme it bends our understanding of physics, a reminder that the universe's reality often outpaces our imagination. That initial clockwork precision, so suggestive of a hand winding it, turned out to be the byproduct of a stellar corpse in a deadly orbital dance, a spectacle of raw, indifferent power. It is in this silence, in the absence of a caller, that we find the true lesson. The journey of seeking, the refining of our tools, and the humbling of our assumptions hold as much value as the final answer itself. So as you sit with the weight of a universe that hides its wonders behind vast distances, remember that every question we ask reshapes the world we live in. What do you think is out there, waiting for us to listen just a little more carefully?